Hello everyone. Today's lecture will be taken by Saee. She is 2024 EGMO bronze medalist, and also this year she selected for EGMO team for India. She is also OMC director, OMC 2.0, and also organizer in SOPI and organizer in Unofficial TC. She is like very cool person, and she as well as math. She also do what you call yeah, computer science kind of thing, like theoretical computer science. And yeah, you will have so much fun with the lecture. Yeah.
I hope so. Okay, I'm very excited and also slightly nervous, but okay. Hello, everyone. So turn your cameras if you have a good enough internet. At any point, if you want to ask something, just unmute and ask. And I think that's most of it. Okay, we can get started. Okay, so mm, the beginning of the story, let's go back. And everything I think started when Hilbert, the mathematician David Hilbert, you've probably heard of him, he was questioning every single thing from the foundations of mathematics. So he posed this question sometime in late 1920s, I think, which was something like, is there a procedure by which we can answer every single question? So, what do we mean by that? So, slightly more formally, is there an algorithm which, when given a statement, it can determine whether it's true or not in a finite amount of time, obviously. So this question was asked, and for the longest time, even Hilbert himself believed it believed that the answer to this is true. So, like for sure, maybe we can't find it, but for sure there has to be some way by which we can just brute force everything in the worst to worst case scenario, right? So, mm, like Hilbert himself is known to believe that the answer to this question was yes. Um, okay, but before we go into answering this question, wait, what exactly is an algorithm? Um, so what is an algorithm, guys?
It's like this set of instructions that you give to a computer and the computer does stuff.
Is
Uh-huh.
it just necessarily to a computer though? I mean, you can perform an algorithm.
Like to,
Great
it's
point.
just a set of instructions then.
Yes, a set of instructions.
Right. Okay, any other things to say about what an algorithm is?
It
Okay.
achieves the goal that we need.
Huh, sorry?
It achieves the goal that we need in a finite number of steps.
Okay, interesting. Mm.
I think
Okay.
we have probabilistic algorithms which take unknown amount of steps as well, or maybe arbitrarily long steps. So I don't know if we can say finite is a good word. Maybe there's something which on
Hmm.
one out of 100 time takes infinite steps. I mean, never ends. That's possible.
Hmm.
I
Hmm.
No,
So,
but how
so
would that?
any, yeah.
No, sorry. I mean, how would that complete our goal? That is, even if it's an arbitrarily long number of steps, at the end there should be some end goal, right? And that would mean that it is finite up to some extent.
maybe not related to an algorithm, but I think Hilbert called it the Einstein-Dunks problem or some German name. It was
Yes.
yeah.
I couldn't pronounce it, but I had it written on my slide here. I don't know how to pronounce it, so I didn't bother. But yeah, that's the
Yeah.
question's name. Okay, so what we want to do is, before we try to answer this question, we want to formally define what we mean by an algorithm. So, uh, all right. So before we go into the actual thing, so this kind of looks scary, right? This is what we're going to get to, but hopefully we will do some less scary things before that. So let's start with something very simple. Let's start with um a machine that does simple tasks for us before we go into defining some harder things. Let me go to my okay, let's just look at this first. So, okay, as of now, this means nothing, but hopefully I'll explain it. So, these circle things that you see, they are called states. So, at every point in time, you will be in one of these three states. Also, we are assuming that our input is going to be a string of zeros and ones. So also this arrow that you see over here, that means this is the starting state. And this, as you can see, is like circled twice. So this is one of the finishing or accepting states. So what is this automata doing? Let's say you want to compute this, like let's say you want to see what happens when we get 1 0 1 0 0 as input. So first we go to the starting state, and now we see, okay, we are reading a 1. So when we are at the starting state and reading a 1, we stay there. Then we read a 0, so we go here because we have read a 0, and now we are at the second the state Q2. And we read a 1, so we must go back. And then we read a 0, so we go here. Then we go read a 0, and then we go here. And now we have stopped reading the input, and we have reached Q3, which is an accepting state. So this string 1 0, we say that this automata accepts 1 0 1 0 0. Right? Is it fine? What this graphical representation of?
Can I just state what's a state again?
Yes, a state is just something to keep track of, meaning initially you are on the starting state, then you read as 1, so you are still on the same state because that's what the automata tells you to do. When you read a 0, so you jump to this state because that's again what the automata is telling you to do, and so on and so forth. So then the reason for the existence of states is that some strings this automata is going to accept, and the other things it's going to reject. So if you end up on Q3, we say that 1 0 1 0 0 was accepted because Q3 is an accepting state. But if you would have ended on Q2, for example, if you would have done something like 1 0, let's say just this was the input, then you would have ended up on Q2. And that's not an accepting state. So 1 0 would be labeled as rejected by this automata. Does that make sense, Aryan?
Yep.
Okay. Okay. Any other questions? Okay. So what kind of, so can you characterize the types of strings that this automata is accepting? So for example, it's rejecting 1 0, but it's accepting 1 0 1 0 0. So can you tell me, maybe it's a
It's
slightly
like
hard
any
question.
string, any string with
Yeah.
greater than 2 zeros.
Exactly. Any string, not necessarily. Wait, is that true?
No, like 1010 is not acceptable.
Yeah,
No, like it needs to have at least two trailing zeros, I think.
exactly. It should have 2 consecutive zeros and then it will be accepted.
Right.
So yeah, that's all. So if it has 2 consecutive zeros at any point, then it's accepted. All right. So this gives us a way of checking whether a string has 2 consecutive zeros or not. Just as a quick exercise, can you make okay, so this kind of automaton is called a deterministic finite automaton. So let me try to explain. The D stands for deterministic, which means at any point if you're at a state, then you should know exactly where to go next. Meaning if I get 0 as an input, I should know exactly where to go next deterministically. And if I get a 1 as an input, then I should know exactly where to go. For example, if I didn't know where to go, if I had 1 when I was at Q2, then that would be a bad thing. So that would not make a deterministic finite automaton. Or if I had, let's say, 2 arrows coming out of Q2, which were labeled 1, then that would also not be a deterministic automaton. So this is not deterministic because it doesn't tell you for sure where to go. So deterministic it tells you for sure where you need to go next, right? Okay. So that's what the deterministic stands for. Finite just means it has finite number of states, and automaton is just automaton. Okay, so just like a small exercise. Wait, sorry. Yeah, can you make a DFA which accepts all strings with at least 2 zeros? So over here we were accepting all the strings where the zeros were consecutive. But can you make a DFA which accepts all strings with at least
Just
at
make
least
the
2 zeros?
one on Q2 loop to Q2 itself, right? That should work.
Yes, true. Exactly. Okay, so these were okay. Any questions before I proceed about what a DFA is?
This is a question related to that thing you're trying to prove or disprove. What we can't we to have problems like find root 2? Obviously, that will take infinitely many steps. I mean, you can't find root 2 and finitely many steps binary expansion. So, what exactly is a problem as well? What do you mean by a problem? Because I'm pretty sure you are not counting find the binary expansion of root 2.
Yes. Okay, so what do we mean by so it's more like given a statement, the algorithm should be able to tell you whether it's true or not in finitely many steps. That's what I mean. It's not about finding anything, it's just about deciding. It's like a yes or no thing.
Okay, sure.
Okay. All right. Okay, so now we've looked at deterministic automaton. So there's a bunch of questions. For example, what are the types of strings that we can, so for example, the rules that were accepted here was 2 consecutive zeros or at least 2 zeros somewhere in the string. So these are things that we can recognize sort of using the deterministic finite automaton. So can we classify all such strings that can be accepted? Or another question to ask is, are there any things that this deterministic finite automaton does not recognize? Or so there's an entire so I won't go into too much detail, but these are just some questions for you to think about. Okay. Also, we looked at deterministic finite automaton. So similarly, what are non-deterministic finite automaton? Right? So non-deterministic finite automaton is again something that everything is the same except now you're allowed to have multiple arrows going out of a state labeled the same thing. But then you might ask, okay, so what does this mean? So if I'm at Q2, I can go to Q1 and I can go to Q3. So when do I accept a string and when do I reject it? So you accept a string when at least if any one of these paths leads to an accepting state, then you accept that string. But if all of them lead to rejecting states, then you reject. So that's the slight change that happens in non-deterministic as opposed to deterministic. So this is like the most simplest model of computation or the sort of algorithm that we have been talking about that can be made. But so as it turns out, it's a small spoiler. I won't spoil too much, but you cannot recognize every single set of every like you can't recognize everything you would want to recognize in this. So there are some things that you cannot, some nice things that you cannot recognize here. So that's why you need some more powerful machine. So that's where you, so there are some, yeah. So that's where the Turing machines. So there's a couple more, I think, machines in between, but let's just skip to Turing machines. So okay, this looks very fancy and scary, but um all it's saying is, so the one bad thing that was there in the finite state automata is you don't really have much memory as such. You're not able to store what you have seen earlier and go back to it and something along those lines. That's the intuitive way to think about it. So Turing machine sort of tries to bridge that gap. And what we have is, along with the finite set of states and the and telling you where to go when you get what input, you also get these infinite tapes where you can write down things and record them and come back to them later. That's the only difference. And as it turns out, and it makes sense also, right? Because if we have like a lot more memory, then we would expect that you are able to do more powerful things. So Turing machines are indeed much, much more powerful than deterministic finite automata. And that is indeed what we will refer to. So when I say an algorithm, what I mean is something that we can run using this Turing machine, run on this Turing machine. don't worry too much about the details of this. If you have understood, like if you have an intuitive understanding, it is fine. So Turing machine is basically the mathematical or formalized version of algorithm, or that's all it is. Okay, so again, Turing machine has a bunch of states and some function tells you where to go, and plus along with the memory. Okay. Any questions about anything so far? Okay. Okay, so now let's get back to the question of can we have an algorithm for every single thing? So as it turns out, the answer is no, and Hilbert was very sad because of that. So this was proved by Turing independently, Turing and Church independently. So I think Church did something in lambda calculus. I'm not too sure about what he did, so I won't go into that. But Turing's stuff was very nice. So in the same paper that Turing defined Turing machines, by the way, you've probably heard of Turing, because he was the one who solved the Enigma, etc., etc. So yes, so he was also the reason. So he came up with the entire idea of Turing machines, and like because of that, the theory side of CS is what we know of today. And in the same paper, he also disproved Hilbert's conjecture, or his question. He gave a negative answer to that and a proof to that. So we will try to look at what he did. So this is the famous halting problem. What does it say? So it says you're given a computer program P and an input I. Can you have a finite algorithm to determine whether P halts on I or not? So what do I mean by that? So there can be programs that run forever, right? I can just say while true, run. So it's just going to run forever because true is always true. And this is a computer, we can just like read through it. We can probably do something to make the computer read through it and see, there's a while and there's a true inside of the while, which is always true, so it's going to run forever. So this we can quickly answer by just looking at the program. But can we do so in general? So given any program and an input for that program, we want to know whether if we run that program on that input, whether it will halt or not. So one minor thing to notice here is like you can't just run I on P to check whether it's halting or not, because if it's not halting, it's going to go on forever, and we can't really know like for sure whether it's going to run forever or not by just running it. Okay.
So the question is, can you find an algorithm which answers this question?
Yes, exactly.
So what if you run the algorithm on the algorithm?
Yes, amazing. That's the idea. So what we not entirely, but yes, that's like the self-reference is the main part of the proof. Okay, so what you will say is we cannot possibly find a algorithm which does this. So the way we prove that is a contradiction. So let us assume that there is such a program, let's call it X. When given the program P and the input I, it tells you whether it tells you a yes, it gives you a thumbs up if it's going to halt, it gives you a thumbs down if it's not going to halt. Right? Now what we say is, okay, we have X, now I will consider construct a new algorithm using X. I'll call it Y, which takes only one program as an input. Then what it does is it calls X as a routine. It asks X to run P on P itself. And then if X reports that yes, P is going to halt, if this is going to halt, then Y just decides to run forever, just by doing like a simple while true run or something. And if X reports that P is going to stop or P is going to halt, then Sorry, that's what I just said. If X reports that P is going to run forever, then Y halts immediately. Is it clear what Y is doing?
Yes.
No, can you repeat once?
Yes. So what we construct a new program Y, which takes only one input, and it asks it first Y goes to X and asks, okay, is this new program going to halt or not? If X says yes, it's going to stop, then Y decides to run forever. And if X says no, it's not going to halt, then Y decides to stop.
Okay.
So basically, whatever X tells Y is going to do the exact opposite of that.
Okay.
And now the self-referential parts comes in. You consider, you give Y as an input to Y. So now if X is going to, okay, maybe somebody else would like to explain this argument from
Can I
here.
try?
Huh.
Okay, so
Yes.
let's assume that X reports that like Y will halt. Then Y is instructed to not halt. And similarly, if X reports that Y doesn't halt, then Y is instructed to halt. So Y is just creating a paradox, no matter what.
Can't we make a
Exactly.
space of programs which all of them halt? Why can't I just make a space of programs in which all programs halt so that no such Y exists? For any P, like for any program, there exists no program that does not halt. Like, why can't I make that happen? Like, not a
Sorry,
Turing
I don't get
computer.
your question.
It's not a Turing
Hmm.
machine, obviously, but why can't I make a
Yeah.
machine in which all programs halt?
How would you do that, and why would
No, I'm
that
saying, why can't
be?
you do that? I'm asking, why can't you do that? Because if you do that, then this counter example won't work, because why no such Y will exist in the
Okay,
first
so
place.
sure. So what you're saying is we force the program to halt after some time, right?
I know, I'm saying that there exists no
Huh.
program which never halts. Which, yeah, I
Yeah,
don't
so
say
all
we force it
programs
to halt,
you
but I'm saying, yeah,
wait, but then that's not interesting. So I'll tell you what makes the halting problem interesting. So consider something like the Goldbach conjecture, right? What does it say? It says that if you have any number can be written as a sum of two primes, right?
yes.
So if you knew, so then you can just write a program which checks brute forces for every number it tries to find two primes adding up to that number. And
By
if
the
at
way,
any point it yes.
yeah, so I was asking that this disproved that the conjecture of input. So is this doable in real life? Like, if you can't make a Turing machine in real life, how does it disprove the conjecture of input?
Wait, I will come to your question later. Let me finish what I was saying. So I was saying, yes, the Goldbach conjecture states that every even number can be written as a sum of two primes. So you can write a program where you go through every single number and you try to find two primes which add up to that number. Now, if at any point you have found a number for which there exist no two primes that add up to that number, then you just ask the program to halt. Otherwise, you make the program run forever. Like you just run the program until you find a number for which the Goldbach conjecture is not satisfied. Right? Now, the thing that makes halting problem interesting is you can just, this program is very easily written. You can just give give X the this program of which I just described for the Goldbach conjecture. And now if X is able to tell you in finite amount of time whether it's going to halt or not, the Goldbach conjecture is solved. Does that make sense? Where is Shreyan? Shreyan left. Sad. But okay, does that make sense to other people?
Yeah.
Yeah, it does.
Right. Okay. So okay, yes. And then there was some other question. I forgot who was asking. I also forgot the question. I think Aryan was
No,
asking.
it's okay. I got the answer.
Okay. Okay. Yeah, so that's what makes the halting problem interesting. And so it doesn't so I'm not sure how useful as such it would be to have programs that like always end. I'm not too sure if I answered the question he had, but okay, let's move on. Okay, so this was very self-referential, and it's all of this business is kind of sus, right? Let's look at some other problem which also cannot be solved, which doesn't seem to have self-referential thing. Okay, so the post correspondence problem, this does not have anything to do with post offices or anything of that sort, as I initially thought. So post is the name of the computer scientist who came up with this. So the question is,
Post.
you're given.
Wait, Post is the name of a scientist?
Yeah. You can look it up later. I've linked everything in this slide, so you can look it up later. So we have, the question is given a set of dominoes, and so there's like a domino is where something like this, and the top and the bottom both is like a sequence of strings. You want to know if there's a collection of these. Repetition is allowed, so you can use one domino twice or more than that if you would wish, or you can use you cannot use a domino at all, that's also fine, such that the concatenated strings in the top and bottom are the same. So that's the problem. And the claim is that this is also undecidable, meaning you cannot have an algorithm to solve this at all. Okay, so just so that just to make sure that everybody has understood this question properly, can somebody maybe try to see if we can have some collection of these for which the
You
top
could
and the
take the
bottom.
You could take
You
the
could
first
take the first two, then you have XYW and XYW.
Okay, yes. I did not realize that when I was making this. But yes, that's an easy solution. Yes, amazing. But the thing is, yeah, so as we're going to try and see, I won't go into the details of this, but the idea is that yes, sorry.
Can't you go through every subset of them and then decide? Like, if there
No,
are.
but repetition is allowed, right? So maybe there's some way that you repeat them and that makes them equal.
Oh, okay.
Yes.
Also, what's the take about?
No, flipping dominoes is not allowed.
Okay.
Yeah. So what is it that makes this problem impossible? So the nice thing, okay, like the idea is very nice. The details part I won't go into, but just the idea is, okay, do you want me to share it right now, or what would people like? Or would you guys prefer thinking
We have
about
a
it?
finite number of dominoes, right?
Yes.
So why
Can you
can't you
just show the
try every
problem
combination?
statement?
Sorry.
Why can't you just try every combination?
No, the repetition is allowed. So you
Oh.
could repeat some dominoes, and that's why it's hard. So okay, so maybe we can come back to this at the end of it. But the idea for this is very nice. In fact, the idea is that we somehow show that solving this is equivalent to solving the halting problem. Okay. So, okay, but we have looked at things we cannot do, but sure, that's all good and fine. But what are some things we can do? So sorting, right? So you guys had some very cool lectures by Archit on sorting. So there's so many cool things we can do. So first we try to show bounds as to, like, first we try to find algorithms and try to do as good as we can in terms of the time complexity. Then can we do even faster? Then can we show that we cannot possibly do faster? Then what are some variations that we can look at and things like that. Another interesting problem is primality testing. Given a number, can you check whether it's prime or not? So this did not have a polynomial time algorithm for a very, very, very long time. So okay, also I haven't defined what I mean by a polynomial time algorithm. Okay, I will switch my camera off because there's no electricity here, and I think my laptop is running out of charge. Anyway, sorry. Yes. So what do I mean by a polynomial time algorithm? is just in the size of the input, the time that I'm taking, the time that my algorithm takes to run is polynomial inside of the input. So if my input is, let's say, total n bits, then whatever the time I'm going to take has to be some polynomial in terms of n. And over here, we can consider some things like addition, multiplication as something that takes constant amount of time, or like one amount of time. So if we have some loop, let's say, which is running n times, and that we say is going to take n time, and so on and so forth. So when from here onwards, whenever I mention polynomial time, it just means that in terms of the input, it should take polynomial time. Okay, so these are some things we can do. Okay, let's look at one of my favorite examples and algorithms. It's a very cool problem. Also has practical application. So vertex cover. So what is the problem? You are given a graph. So let's make a graph. You're given some graph, and you want to find a subset of the vertices so that it's the smallest possible set, and also every edge is sort of covered, meaning imagine these vertices as some corners or something and the edges as roads. So you want to place watchmen on the posts so that all the roads are covered. So for example, I could place a watchman here, I could place a watchman here, and I think every single no, the road is not covered. So maybe I'll need to place another watchman here. So this is one valid vertex cover, right? So is that fine? Is it fine what a vertex cover is? The objective is to find the smallest possible vertex cover because we're very confused people, and we want to minimize the amount of cost that we incur. So we want to place as less watchmen as possible. Right? Is the question okay?
Yes.
Oh, amazing. So maybe I'll give you guys some 1-2 minutes to think, and maybe you can try to come up with an algorithm to do this.
In the example which you gave, is 3 the minimum? Or we
I
can
don't
place
know.
lesser?
I don't know. Is it? Can somebody help me out with that?
I think 3 is the minimum.
Okay. It looks like the
Uh,
minimum.
Yes.
Is the minimum.
I mean, the weird part is that whatever algorithm you come up with, if it has some n watchmen, you need to show that n minus 1 watchman just isn't possible no matter what.
And just brute force.
No, how long will brute forcing take? That will take too long. We are now looking at things we can do. And if we are able to do it, then you want to do it fast, obviously. So the thing about this is, okay, vertex cover we can do because, as Shreyan said, we can brute force. But that's a very, very, very slow solution. Can we do it faster?
We arrange the
It's
watchmen
fine
in
if you don't have the proof for now. Even if you have some algorithm idea, that will be amazing.
Maybe like look at the vertex with maximal degree, place a
yeah,
watchman
and
there,
place the
and
watchman
then
there, yeah.
work on the
No.
remaining graph.
That
would
would always
be
be the best case, I guess.
that
I
would
guess
be
the
a good
main thing
idea.
is to take an account of what vertices we haven't covered yet and find the optimal position there. So we're kind of pinpointing slowly and slowly with each watchman.
In this case, we can always put that rightmost watchman because we have only one node attached to it, right? So if we ever have just one node attached to a guy and one edge, we can always just put our watchman on one side.
That makes sense. Yes.
So basically, any leaves will have a watchman adjacent to it.
Yep.
Interesting. Okay.
Because leaves aren't that optimal to put watchman.
That makes sense.
Okay, but I think still like in general we should try to go for vertices with high degrees because
Yeah, like
it's cut down on our
maximum
roads by a lot.
degree, then the second maximum degree, like greedy stuff, I guess.
Like not exactly
Yeah, yeah.
second maximum degree, but maximum degree, then maximum degree in the induced subgraph when you delete that vertex and so on.
Yes,
But
yes,
of
yes.
course, there's
Hmm.
the issue that then you have the thing with leaves and you have to deal with that. And what if there's very low degree over there? But then the
Fair enough,
question
fair enough.
becomes, does that even matter? Like eventually we
Hmm.
will reach to that area, so why do we care? Is the question.
Right, right, exactly. Hmm. So, okay, so we've already discussed this. So I was just trolling. Anyone who comes up with an efficient algorithm for this gets $1 million. So if you guys can solve this question in polynomial time, you will be getting $1 million. And I want at least half of that because I introduced you to this. Okay, so some time I want to spend on getting to know why solving this question will give you $1 million. And I mean, this looks like a pretty like doable question. I don't see what's like that hard that we cannot come up with a good enough algorithm, right? Like,
The issue is
I
efficient,
mean,
right? Like
Lots of people, lots of nodes
yes,
have
efficient.
multiple interactions. The interactions are weird
Hmm.
between people. That's the
Hmm.
difficulty.
exactly.
You can have knots, like
Right.
once that something is covered, then you have to remove it. But
Hmm.
that's the issue.
Right. Okay. So let me try to explain why solving this will give you $1 million. So what we're going to try and do now is um classify hardness of problems. So till now we were only classifying according to whether we can solve a problem or not. But now we are saying, okay, whatever we're not able to solve, that's fine. But if we are able to solve, then can we classify the problems using their hardness? So obviously we've already defined some set called P. That's just the set of all problems that our Turing machine can do in polynomial time, in terms of the input. Um, so okay, let me just get into this. So there's the most controversial or like the main two sets that are interesting. Okay, not interesting. That define this $1 million question. You might have heard of this question before, P versus NP. It's one of the $1 million questions posed by Clay Mathematical Institute. That if you solve them, you'll get $1 million, obviously. So um, let's try to understand what exactly the question is asking. So it's saying so in the question you will see there's something called P and something called NP. So P is, as you might think, is not just polynomial time. It means deterministic polynomial time, which means it's the set of all questions which a deterministic Turing machine can solve in polynomial time, right? And NP is not non-polynomial time, it's non-deterministic polynomial time. Meaning, if you have a non-deterministic Turing machine, then uh, then what all can we solve in polynomial time?
Wait, what's the
That
assumption with time here? Like if there's multiple options, will a computer go through it one by one or will it go through all of those at once?
no. So the non-deterministic Turing machine is not something that we can. Okay, that's actually the question about it. So whether we can, so the kind of machines that we can make in real life are Turing machines. The question of whether or not we can simulate a non-deterministic Turing machine using a Turing machine is this $1 million question.
I
So non-deterministic Turing machines, as of now, is something that only exists in theory. We don't know about real life. So if you can make a non-deterministic Turing machine, then this problem will be solved, right? So just to do a quick recap, what is a non-deterministic Turing machine? It's when you can go from one state, you can go to multiple states on the same input, and if even one of these paths lead to an accepting state, it's going to be accepted. Otherwise, if all of them reject, then it's going to be rejected. Okay, so the question of P versus NP asks us whether adding non-determinism gives you additional power or not. So I'll talk more about this in a while, but this is a quick sanity check. What can we say about the sets P and NP? Can we say anything at all?
P belongs to NP.
Exactly. P is a subset of NP, right? because everything that you can solve, everything that you can do on a deterministic, like deterministic Turing machines is just a subset of non-deterministic Turing machines. The question is whether we don't know whether it's a strict subset or not. That's the $1 million question. Okay, everything fine so far? Okay. Okay, so this is the $1 million question is, does non-determinism give Turing machines more power? Okay, but now you might think, okay, why is this a non-trivial question, right? Because clearly non-determinism seems to be adding so much more power to our set. But the reason it's not trivial, I'm going to spoil something from earlier actually. So you remember finite automata. So we have deterministic finite automata and non-deterministic finite automata. As it turns out,
They're one and the same, basically.
exactly.
But
They are indeed.
But at least
Hmm.
the thing I did to prove it, NDTA are up to 2 to the n times as big as DTA. I mean,
Yes,
DTA
yes.
of the, so like a power of 2. The speed is slower, or the speed is increased by NDTA, I guess.
Yes, that's true. That is indeed true.
I mean, the ability to do stuff is the same, and I'm sure that everything a NDTM can do, or DTM can also do, but the speed should also.
Okay, yes, that's the point. Yes.
The number of states has increased, but I think the time it takes is still polynomial, because in like if the non-deterministic thing was doing it in O of n, then even now it should work in O of n.
You can just do brute forces efficiently using NDTM. Like you can just say, put it in all possible states for the second one, then put it in all possible states for a third one, then put it in all possible. It grows exponentially the number of things you are choosing, like checking at one time. So I'm pretty sure you can do that for NDTM, right?
Yes. Yes. Okay. Let's not think about this stuff with finite automata. Okay. Sorry about that. Yes. But yeah, as it turns out, this is a very, very, very hard problem to solve. Okay. Okay, so there's another way to look at NP. It's the think of it as the set of problems that we can possibly hope to solve. So what does that mean? It means that if okay, also one thing I should have probably clarified is when I'm saying P or NP, the questions we are asking are all going to be decision problems, meaning the answer has to be yes or no. So for example, like even so the reason for that is because if we are reaching an accepting state, then that's sort of like a yes answer, and if we are reaching a if you're not reaching an accepting state, then that's sort of like a no answer. So the questions from now on, every single question we look at will be rephrased so that it's a decision question, meaning the answer is either a yes or no. So now the thing is we want to so as it turns out, NP is equivalent. So non-deterministic polytime is also equivalent to showing that if the answer to your question is yes, then you can show, or you can, okay, let's say I have a vertex cover problem. I have some graph and I claim that the answer to this is okay. Let's just look at an example. Sorry. So the thing is, okay, we are given, again, we're going back to the vertex cover problem, and now we have rephrased it so it's a decision problem. So instead of saying, okay, find the minimum, I'm going to ask whether there is a vertex cover with size less than k, where I'm taking k also as an input, right? So now what I'm claiming is, okay, I asked this question to Shreyan, and Shreyan says the answer is yes. Then if Shreyan can prove it to me in polynomial time that the answer is indeed yes, then that's an equivalent condition to vertex cover being in NP. Meaning if the answer is yes, then there should exist a proof that is verifiable in polytime. So for example, the proof sort of for vertex cover will just be to, okay, and now I'm asking Shreyan. Shreyan, like give me a proof for why there exists a vertex cover of size less than 5. And Shreyan can just give me that vertex cover and be like, look, this is the vertex cover of size 3. 3 is less than 5. Now I can verify whether Shreyan's vertex cover is actually a vertex cover or not in polynomial time. Because now I can just go through all of these, because now I can just go through the vertices that he has given me, or I can just go through all the edges in the graph and check whether they are all covered or not, right? So for example, let's say Shreyan gives me this, okay, this does not have a thing of size 3. Let me erase this. Shreyan gives me this and this and this. Then now I can verify that this is a vertex cover because I can just go to every single edge and ask, okay, are you covered? This edge is covered. This edge is indeed covered. This edge is covered. This edge is covered, and so on. So I can verify that Shreyan's answer is correct in polynomial time. So if I'm not even able to verify Shreyan's answer in polynomial time, then I can't even, the way I think about it is that I can't even hope to solve it in polynomial time. So NP is sort of like the set of questions that we can
Like,
hope to
is it
solve.
is it possible to like solve it in polynomial time but not being able to verify it in polynomial time?
No, that's a great question. If we can solve it in polynomial time, we can verify it in polynomial time.
Just use
And
the
I will
solution.
leave you to think about it.
Just use the solution. That's what we say, oh, we solve it, and since our solution works, this is the proof.
Sorry.
Like, do you consider solving it yourself thing a possible verification?
Yes, sure. Like if you can solve it in polynomial time, then you can also verify. That's not a hard thing to prove. Like I'll leave it as an exercise for you. It's
Yeah, like what I'm telling is that if you can solve it in polynomial time and you want to verify, you can again solve it to verify. So does that count?
sure. Yes, that's exactly in fact the argument.
But
Okay.
yeah, NDTMs won't be used. For example, you can't say that this is the minimum. How would you prove it is the minimum? Like I can show it works, but how would I show it's the minimum thing that works?
Okay, Saee just left the meeting. Let me check with her. Okay, let's wait for a few minutes. It's probably some internet issue.
The vertex cover thing is on simple graphs or on the graph which have loops and all, and two edges between two points.
Saee is saying that she's joining back. Her laptop died, so she's changing device.
Vishal, can you tell me if the question was on two edges? Like if I have two nodes, can I have two edges between them, or do they have to be one
There's
edge
a
between them?
graph, but I don't think too much changes, even if you make it non-simple. But yeah, simple itself is hard, yeah.
Are the questions equivalent, simple and non-simple, or are they just both hard by coincidence? I'm not coincidence, but you get what I mean.
Will matter. We just here the same, right?
What?
Are you talking about the project?
Vertex cover, right? We're talking about vertex cover.
Yeah, I mean, if there are two edges between a single vertex,
Then like they're treated the same. So
yeah,
both are equivalent.
you can just ignore.
And also loops will just make it easier because if you have a loop, we know there must be a point, vertex at and what's at that point.
Also, maybe we should like pause recording.
Hi, I am. Okay. Okay. Yes. So I think we were discussing that vertex cover is indeed can be verified in polynomial time. So it is in NP. Also, there's a you can try to think about this problem also as to why it is equivalent, why these two definitions are equivalent. So why does having a polynomial time proof, verifiable proof, why is that equivalent to being able to solve it on a non-deterministic Turing machine? Okay. Yes, but now back to the question. I still haven't it's still not known whether why does solving sure vertex cover is hard, but why does solving vertex cover win us $1,000? Right? We know a vertex cover is in NP. There's one problem in NP that we have shown to be in P. That's not telling the question still stands. There are so many other questions which we don't have, which are in NP, which we don't have polynomial time algorithms for. Right? So okay, here's the fun part. The thing about this is there's another set called NP complete. So intuitively, the way I think about it is it's a subset of the hardest problems in NP. What does that mean? It means if you solve a problem which belongs to NP complete, by solve I mean solve it in polynomial time, then you can solve any problem in NP in polynomial time. Just take maybe a few seconds to appreciate
How would we prove that?
the
How would you
power.
prove
Like
complete?
any problem, no matter like what field or what it's involving.
Yes, any problem that belongs to any problem in NP.
How would you go about
Like
proving
any
that?
problem,
I will talk about, yeah.
like any problem in NP, I guess technically covers all the problems in the world.
You
I
can
would
have
assume.
Not
Like
really. Like
you can have
we
n
saw
exponential.
the PCP problem or the halting problem. These are things that don't come under NP. And there could possibly be some problems that are not even verifiable in polynomial time. That will not come in NP.
alright, so it's like these problems are verifiable in polynomial time, but not yet sort of solved in polynomial time.
Exactly, yes.
Okay. And
So
there are some problems which are not even verifiable in polynomial time.
yes. So now the very nice thing about this is that if you solve any one single problem in NP complete really quickly, then you can solve every single problem in NP really quickly. And that I think is insanely cool. So now we're sort of, when I say this is like the subset of hardest problems in NP, I'm now comparing the hardness, right? So what do I even mean by comparing? So let's try to do a short exercise. So hang on. Let me make a OneNote and share it. So what we will try to do now is show that the problem of finding the maximum possible clique. Sorry, this device I'm not used to. Yeah, the problem of finding the maximum possible clique is equally hard as finding a vertex cover. So what do I mean by that? Is that if I have a fast enough algorithm to find a big clique, then I have a fast enough algorithm to find a small enough vertex cover. Is it clear as to what we want to show?
Yes.
Okay. So how could we go about showing that? Let's try to do
Some
some.
sort of weird bijection maybe between like a small clique and like I don't know. So between
Yeah,
like a
yeah,
large
let me
clique and a small vertex cover.
let me state the problems first. So you're given G, 2 comma E and K, and you want to know if there exists a clique of size at least K. What is a clique? Clique is just where a complete graph where all the vertices, every pair of vertices is connected by an edge, right? And again, we have seen this problem before. I just write it down. C is V comma E. And you have given K. Does there exist a vertex cover of size at most K? Let's try to do something more straightforward first. Can you say anything? Okay, let me define another problem. We call this intersect. So given graph G is equal to V comma E and K, does there exist an independent set of size at least K? What is an independent set? It's the exact opposite of a clique, meaning an independent set is a subset of the vertices so that no two of them are connected to each other. For example, if I have this, then this is an independent set.
So it's basically the complement of a clique.
Exactly.
So basically, if we just take the conjugate of a graph and do the
Exactly.
clique one, we get the inset one.
Exactly. So now it's not hard to see that clique, and if you can solve clique really fast, you can solve independent set really fast. Because what you can do is get a graph and sort of reverse it or take its complement. Meaning if you had this graph, then just look at every pair of vertex. If it originally has an edge, in the new graph, it should not have an edge. If it originally does not have an edge, then add an edge between the two things. So now the complement graph will look something like this. And now the task is, and now in this complement graph, we know we can find clique really quickly. So the clique in this new graph will correspond to an independent set in our original graph. So if we can solve clique really quickly, then we can solve independent set really quickly. By really quickly, I mean in polytime. And the argument other way also works the same. So if you can solve independent set in polynomial time, you can solve clique in polynomial time as well. Notice that the crux of this is that we can do this change of graphs in polynomial time. That is why if you can solve one problem in polynomial time, the other can also be solved in polynomial time. Right? And now can you somehow extend this argument and show that vertex cover is also equivalent?
So won't the largest independent set also be a vertex covered?
But I don't think so. But you're close. We notice that we want to find the smallest vertex cover.
The other side of the clique, as in the complement of the independent set, will be a vertex cover then, right?
Exactly. Amazing. So if you consider the vertices, let's say you have a big independent set, then if you consider all the vertices not in the independent set, then these vertices are going to form a vertex cover, right? Because any edge that is there is going to be across this.
So
There
we
is not
want,
going to be any edge like this.
so
So
the
if you
two
just
cases are
consider
different.
all of these, then it's going to be a vertex
So the
cover.
two cases are different.
Huh?
The two cases are different.
What are different?
There are two cases, inset K and what do you call it? There are two different Ks. One is the inset K and one is the vertex
Yes,
cover K. Those
exactly,
are two different
exactly.
Ks.
Exactly. We can change the case as we want. So if we have an algorithm to find a big enough independent set, then we can find the small enough vertex cover
But how would you
by
do
maybe
it?
setting k as n minus k or something. That's the idea. So the details I want to do some more things. I don't want to go too much into the details of this, but do you sort of get the idea as to how we can show that two problems are equally hard? or even like how one problem is at least as hard as the other problem. Meaning if you can solve one problem, then that allows you to solve some other problem as well by maybe changing the input a little.
I mean,
Right?
they're equivalent, right? So shouldn't like one, if you solve one, it implies the other.
Exactly. So now that's the idea behind the set of NP complete problems. So if you can solve one, then you can solve a bunch of other problems. But wait, I still haven't given you the full story, right? I'm saying if you can solve one, then so if I can show that clique is NP complete, then I can be sure that vertex cover is NP complete, or vice versa. If vertex cover is NP complete, then clique is NP complete, right? But does somebody like spot like what's the question that I'm sort of avoiding here?
Which how to show that even one is empty complete.
Exactly. You need to start somewhere, right? Like once you start, then maybe you from a chain of equivalences or chain of some things, we can show that a bunch of other problems are NP complete. But how do you show that that one problem? You need to start somewhere. So what is that? So the first problem that was shown to be NP complete is the Boolean satisfiability problem that some people were discussing towards the beginning of the class. So in the Cook-Levine theorem, Cook and Levine came together, I don't know in what year, but they showed that the problem of Boolean satisfiability, if you can solve that in polynomial time, you can solve every single NP problem in polynomial time. So what is this problem? Basically, if you're given a logical expression, meaning you're given a bunch of variables, let's say x1 and x2 and x3, or something like x1, not x1 and x2, or some expression like this. You want to know whether there is a way that you can set true or false values for each of these variables so that this expression evaluates to true at the end. Is the question okay?
Yes.
So that is the question. And if you can so there's actually more cool stuff here. There is a way you can formalize this, and you can show that any such problem is equivalent to basically having something like this or
It has to be
this where
polynomial on what?
huh?
It has to be polynomial on what?
Sorry, I could not hear what you said.
It has to be polynomial on what?
Good question. So the
Polynomial is the number of variables, surely. Like
no,
you
so
might
the
have given
input
a
is
large
the input is going to be this expression is you're going to get this expression as input.
Okay.
So
So the
the
size of the
number of
input.
bits you need to, yes, the size of the input. So this question, as it turns out, so there's actually like a lot of very cool theory in this also. You can look this up later, the satisfiability problem. But they showed that this is, I won't be going into the proof, but you can definitely look up things. It's definitely an understandable,
Wait,
if you put it on somewhere, you can,
so like, did you discuss like how if you solve one NP complete problem, all other NP complete problems are solved?
Yes, so this was the first problem that was shown to be NP complete. So I won't be showing that, but if you are interested, you can look it up, and it's really nice. So the idea is that any problem you can encode as a bunch of things as the satisfiability problem. You can sort of encode it as that. I'm not doing a very good job of explaining it, but it'll be best if we discuss this later. But yeah, so this was the first problem that was shown to be NP complete, and then later some other problems were shown to be equivalent to this, and that's how we got the set of NP complete. Okay. So the objective also, I would like to say, of this class is not necessarily to do a lot of math and like do a lot of proofs or something. It's just to sort of get you interested in this field, and then you can look up the proofs or you can try to come up with the proofs yourself. So I hope you're getting curious about all of these things. Okay. So now we have shown that, okay, these problems are insanely hard. Actually, I think a lot of people, most people believe that P is in fact not equal to NP, meaning we cannot possibly find fast enough algorithms to solve these problems. So what do we do now? Okay, also just a side note, problems being hard is indeed useful. Does anybody know about this? Uh, how could we possibly make use of the fact that this problem is hard to solve in polynomial time? So in fact, the entire field of cryptography is based on the fact that you cannot factorize numbers quickly. And that is exactly why all of your banks and everything is secure right now. So problems being hard can also be used in this way.
Is integer factorization just NP or NP hard? NP complete?
I'm actually not sure. Maybe somebody else can comment on it. Is it NP complete?
I don't think that's even known. Like it's also not like a yes or no problem. So
Oh yes, true.
Problem
Okay.
is hard. You could look for an approximation algorithm.
Yes, exactly. So if a problem is hard, then we try to approximate it. And what do I mean by approximations? Again, my favorite example, vertex covered. So the idea is, okay, we cannot find a quick enough algorithm to find the smallest, but okay, maybe we don't want the smallest. If it's like in a reasonable amount of, so if it's, let's say, at most twice the smallest, then also I'm happy with it, right? So can we do that? The answer is yes. So we can indeed find two approximations for a vertex covered. In fact, if you end up you'll be surprised as to if you end up doing sort of seemingly stupid things, they actually turn out pretty nice. So I'll just give this away. So first, the idea is to look for maximal matching, not the maximum matching. What do I mean? Okay, so first, what's a matching? Matching is a subset of the edges so that no two edges have a vertex in common. So this is okay. Matching is subset of the edges such that no two have a vertex in common. Right? And what do I mean by maximal? It just means that I cannot add any more edges to it. So not that I'm not interested in the maximum matching. Maximum matching would mean the matching that has the maximum possible number of edges. I'm only interested in the maximal matching, which means I want to add as many edges as I can until I can't add anymore. Right? So let's consider an example. Something like this. So one example of a maximal matching here would be something like 1 and 2, right? Now we can't add any more edges to this, right? Okay, now any ideas as to what we can do with the maximal matching?
Can we find a maximal matching polynomial?
Great question. Can you for now trust me on it? It's not too hard. Like you can just take an edge and then remove all the vertices and remove all the edges incident on those two vertices, and then again pick an edge, remove all the vertices incident on it, and keep on doing this until you can't anymore. Right?
Can you repeat?
So the idea is you can pick an arbitrary edge, delete all the edges incident, delete the two vertices that are incident on the edge, and repeat this process.
And you can do it for arbitrary edges. That's worse.
Sorry?
That gives a maximum matching.
No, I'm not asking for a maximum matching. I'm
Oh,
only
I
asking
see.
for a maximal matching.
That is got it.
Yeah. Right? Okay. Any ideas about what we do after this? How could we use the maximal matching to find a vertex cover?
What do you mean to approximation?
Yes, great question. So what I mean by a two approximation is that the number of vertices I have in my cover should be at most twice as much as in the optimal cover.
And why can't I just take one watchman at the end of an edge of a maximal matching?
Sorry, I can't hear you properly. Can you say that again?
Why can't I take one watchman on every end of an edge of a maximal matching?
In fact, you don't even have to take only one, because then you have to worry about some more things as to whether we're covering all the edges or not. Just do the stupid thing and take both the vertices.
Yeah.
Yeah. You take both the vertices from every edge in the maximal matching. So now what this will return is the vertex cover that this will return will be this, and this. And I claim that this is indeed a two approximation, meaning that this cannot be more than twice the number in the optimal solution.
Because the maximal matching will require at least one on every edge.
Exactly. So the idea is, in a vertex cover, at least one vertex from all of these edges has to be there in our vertex cover. Because if no two of these are there, then this edge won't be covered, right? So that's why our even God's vertex cover would have to have at least one from each of these, at least one vertex from each of these edges. Which means we haven't done worse than twice as much as God's solution. Any questions about this?
Can we make arbitrarily small approximation values? Can we get 1.5, 1.25, 1.15?
Yes, amazing. So this is like the entire field of approximation algorithms, where you can, in fact, there's a very cool thing where you can get a 1 plus epsilon approximation for any epsilon you want, but then your runtime will be dependent on epsilon.
Will it be a polynomial?
No. It will have epsilon as
If you ignore epsilon, will it be polynomial?
Yes, if you take epsilon as constant, then it will be polynomial. But it could still be like a huge thing. But yeah, that's fine. There's like this is like some more cool things that you can do in approximation algorithms, where not only you have constant factor approximations, but you also have what do you say? Like, you can get as close to one as possible, but never actually reach one. That's some cool stuff. Then, in fact, there are some problems which you cannot even hope to approximate. Because if you even get like some constant approximation for it, you will have P equal to NP.
What's the example of such a problem?
I think, okay, I don't want to comment anything wrong, but I will look this up later and I will tell you. Which that is also very, very cool. Like, some problems are just too hard. You can't even approximate them. Okay. There are so many more things you can do. So, for example, we looked at polytime algorithms. Then there's something called exponential time algorithms. Then, sublinear algorithms which take less than O of n time. So nowadays, what you have is you have huge amounts of data to deal with, right? The number of
Doesn't it take n time to just read the data?
Exactly. So nowadays, people are also very interested in finding algorithms that do even faster. Like, you're not even allowed to read all of the data, but still do it. So that involves a lot of randomization, and then you sort of go into the model where you want to get the right answer with high probability, or you want to get close to the answer, as close to the answer as possible, things like that. So there's an entire field of sublinear algorithms. Then there's also some quantum. So there's the entire field of quantum computing where you use properties in quantum mechanics like entanglement and interference and stuff to get. So in fact, if you have a quantum computer, then you can factorize things really quickly. So if at any point in the future, if we get an actual quantum computer running with little noise, then all of our
Cryptography is screwed.
exactly.
No, like I always had this question that what is that quantum computer at IBM? Is it not a quantum computer?
It is a quantum computer, but I believe it is not big enough, and also it has a lot of noise. But do not take my word on it. Don't quote me on it. Yeah. But yeah, it is a quantum computer, but it's not
Nah,
big
like
enough. And yeah.
it's like people are saying that quantum computer, any country which gets the quantum computer will be in an advantage, but IBM already has a quantum computer, so I was confused.
Yes, but it's not a very helpful
Can't we
quantum
just
computer.
use is it quantum computing just linear algebra? I mean, can't we just do that with actual water waves instead of quantum waves?
Okay, I cannot comment on this, so I will change the topic. Maybe somebody who knows can comment on it later. And then we also have, okay, another one of my favorite things is randomized algorithms, where you, as I said earlier, where you are given the freedom to flip coins. And no, wait, it's not flipping coins.
Like
What's it called?
on average, it will
Toss
give
coins.
polynomial time,
Yes.
right?
Yes, so either the running time is polynomial time, or the running time could be still deterministic, but your answer will not be right. So there are different models of that. Like where one model is where you only expect if the answer is no, then your algorithm must output no with probability 1. But if the answer is yes, then you are allowed to have a high probability, like some less than 1 probability, but it still has to be high. And then so there's another model where you're allowed to have errors in both the cases, but then the errors have to be again bounded and very small.
Are there randomized polynomial time algorithms for halting?
For what?
For halting?
Oh, I am not sure. That's a good question. I'll have to think about it. What do you
I would
mean?
expect
Huh.
no, but how would I do it? Because maybe you can just say with high probability this thing halts, or with high probability this thing does not halt.
How would you even like define? It's a scuff thing. Think about. We will talk about this later. I think we are almost out of time. Anyways, okay. Yes, and also, okay, one last thing is that all of these, there are like much more of these complexity classes, and they're all interlinked, meaning, again, like, yeah, we don't know whether, okay. Yeah, so showing some properties about, let's say, the randomized poly time, this RP and BPP, their relationship with P and NP is actually leads to proving P equal to NP or P not equal to NP and things like that. So we don't so you don't necessarily, if you want to get the $1 million, you don't necessarily have to show something about P and NP. You can work with something like randomized RP or BPP and then indirectly show that something about P and NP. So there's been a lot of very cool work that's happened on this. I will share some resources where you can read about it. There were some more things that I wanted to do, but I don't think there's enough time. But thank you. I hope this was fun. I hope I didn't say anything majorly wrong. And I hope at least now you're like sort of interested and curious to know look up more on this field. Feel free to contact me on Discord, and this is my email, and this is some books that I read at some point and they were nice. And some maybe like Rohan Bhaiya or Rushil can suggest some other resources. That's all. Thank you so much for listening to me and being so active.
I could
This
not,
was really fun.
I sadly could not hear the full answer to the first thing about algorithms in spaces which are not, which have all algorithms having which halt. How would you work in?
Wait,
How
wait,
would
wait.
you?
We will talk about it after we stop the recording.
We were talking about PCC, by the way. The PCP. You said we do it at the end.
Oh, yes. Okay. So the idea is for PCP, what you do is you sort of, so remember Turing machines, you have states and you have inputs and then you go somewhere and things like that. So what you do is you um write down, you define dominoes in this manner where the first domino is like this. The second domino is basic, like every domino is consists of currently the state you are at, and in the below it will show what state are you going to go after this.
Okay.
So this is sort of equal to this and this is equal to this and so on and so forth. Now if the program is going to halt, so and then there's like, okay, this is very vague and there's so many details to figure out in this, but the point is that if it's going to halt, then this will indeed have a solution. The PCP will have a solution because you can just consider this and the things on the bottom will equal the things on the top. And if it's not going to halt, then it will not have a solution. So there's like, as I said, there's more details to figure out to make sure that this is indeed satisfied, but this is the general idea to show that this is, if you can solve this, then you can solve the halting problem as well. Okay.
Yep.
Whatever computation on real numbers, like real numbers will take infinite time to do stuff on if we do these finite memory models.
Yes, I believe there are some models for that as well, but I have not studied them, so I cannot talk about them. Okay, if there's anything else. Okay, thank you so much. This was super fun for me, and I really enjoyed, and I hope you enjoyed as well.
Very fun class, very fun.
Oh,
Yes,
thank
thanks
you.
a lot.
Thanks.
It was
The
really
class
helpful.
was great.